Hi there, this is Empirical Pythagoras, the three calculus enthusiasts. Among all the bells, we like the bell curve most, so we decided to focus on learning the bell curve, also called normal distribution, and prove its empirical rule using integrals. First of all, the bell curve is a function that represents the distribution of many random variables as a symmetrical bell-shaped graph. The normal distribution curve can be written as the function of the probability density function. For the empirical rule, we also study what the empirical rule is about. The rule states that around 68%, 95%, and 99.7% of the data falls within 1, 2, 3 standard deviations, respectively. Looking at how the empirical rule is illustrated, we see how it is constructed. The data falls into 1, 2, 3 standard deviation is the area under the curve from mean minus sigma to mean plus sigma, mean minus 2 sigma to mean plus 2 sigma, and so on. Therefore, to calculate the values of the empirical rule, we integrate the probability density function of the normal distribution on 3 deviations. We use 2 methods of integration, antiderivative and numerical integration.
Let's first try to integrate the function using antiderivative. First, apply by U substitution. What we have here is the function for the area under the curve on 1 standard deviation, on 2 standard deviation, and on 3 standard deviation. This integral is non-elementary, so we have to approximate it using numerical methods. Let's begin with the left-hand Riemann sum. The idea of using left-hand Riemann sum is to draw n rectangles with width of delta u and height of fu that touch the left of the curve, then calculate the total areas of the drawn rectangles. We have the integration of fu du from -1 to 1 is the function here with delta u ui to form the function of fui. Hence, the integral of fu du will be the sum of fui from I equal to 1 to n. The following steps are applied similarly to calculate fu du of intervals from -2 to 2 and -3 to 3. Moving on to trapezoidal rule, the idea of using trapezoids is to divide the area under the curve into n trapezoids with width of delta u, then calculate the total areas of trapezoids. We have the integration of fu du from -1 to 1 is the function here with delta u ui to form the function fui, and the following steps are applied similarly to calculate the intervals from -2 to 2 and -3 to 3. The last numerical integration method that we try is the Simpson method. Simpson's rule calculates area under the curve, provided that the number of n is even and the coefficients are 1, 4, 2, 4, 2, 4, 1. The equations to measure the area of fu is from -1 to 1, we have the function here with delta u and ui to form the function of fui. And the following steps are applied similarly to calculate fu's with interval from -2 to 2 and -3 to 3. Now you may wonder, how could we compare these areas on 3 deviations with the total area under the curve? If curiosity can kill the cat, let's be the dead cat now until we learn multivariable calculus. For now, please accept that the total area under the curve is 1 regardless of mean and sigma. As such, the empirical rule now become on 1 standard deviation, on 2 standard deviation, and on 3 standard deviation.
For the application, the normal distribution bell curve is frequently used to evaluate the exam score. If the distribution of the exam score is normal, the exam paper is qualified for the assessment. While the history score data in the National High School exam in 2020 is similar to the bell curve, our midterm score does not fall into any special distributions. Why? Can we conclude that our exam is too easy or hard? That would be unfair. Sample size for calculus is significantly small, which is approximately 60 compared to the national exam.
Using our program, we generate approximately 68%, 95%, and 99.7% as the percentage of data within 1, 2, 3 standard deviations of the normal distribution equation, which is aligned with the empirical rule. The results become more precise when n gets larger, and Simpson's rule is expected to provide the most accurate estimation. However, our results suggest that trapezoid technique is the most accurate.
To the end, our group has a great time learning about the bell curve and the empirical rule together. Keep learning calculus to be able to calculate the total area under the bell curve.